12. Methane and perchlorate ion are both described as tetrahedral. What does this indicate about their bond angles? Well, tetrahedral means you've got a 109.5 degree bond angle, right? So 4 bonded pairs, no lone pairs, tetrahedral arrangement. Ammonia molecule is trigonal pyramidal, while as boron trifluoride is trigonal planar. Which of these is flat? Well, trigonal planar means flat. So with ammonia, you had that lone pair pushing those bonded pair down more than another bonded pair would. So instead of 109.5 degree bond angle, you got 107. Lone pairs push harder than bonded pairs. And with the best way for the electrons to get as far away from each other as possible when you have 3 bonded pair, no lone pair with boron trihydride, is to get 120 to each other. Again, this is all about electron pairs trying to get as far away from each other as possible, right? The VSEPR model, valence shell electron pair repulsion. In which of these molecules or ions does the presence of non-bonding electrons produce an effect on the molecular shape? Assuming they are all in the gas state, right? So they're all by themselves. So looking at A, silicon tetrahydride, we just, count up the valence electrons like we did last chapter. It all starts with drawing a good Lewis dot structure, right? So I have 8 electrons to play with. I bond everything together. So 4 bond a pair around the central atom. The best way for them to get as far away from each other as possible is to pucker out into a tetrahedral arrangement, 109.5. So we have no non-bonding electrons here to affect the shape. Looking at phosphorus trifluoride, count up the valence electrons, 21 for the fluorines, 5 for the phosphorus, 26 to play with. Bond everything together. That's going to subtract 6 from my pile. Now, when I complete the octets for the fluorines, I have 2 electrons left over, right? That goes to the phosphorus. So that lone pair is going to push those bonded pairs down into a trigonal pyramidal arrangement, right? 107 degree bond angle. So yeah, we have 1 non-bonding pair of electrons shoving those bonded pairs away from it, right? More repulsion with the lone pair than the bonded pair. With hydrogen bromide, he put the electrons in, complete the octets for the bromine. There is no geometry here. I mean, important to understand. 2 things bonded together is not a geometry. You're not going to get a bond angle. So, no, these lone pairs have no effect on anything, right? There's no geometry for them to push on here. If we do the Lewis dot structure for hydrocyanic acid, right? 10 electrons to play with. -4 for bonding everything together. Complete the octets for the nitrogen. I've got a lone, both of those pairs to complete the octets for the carbon, so I end up with a triple bond. So the lone pairs on the nitrogen have no effect on the geometry, right? The central atom here is the carbon, right? So this is going to be a 180 degree bond angle due to the fact that triple bonds push just as hard as a single sigma bond. So the best way to get as far away from each other as possible is to align up 180. We do sulfur dioxide, 18 electrons to play with, bond everything together, 14 electrons yet to be assigned. The oxygens get them first. 2 left over goes around the sulfur. All right, so I haven't completed the octet for sulfur, so I'm going to have to lone a pair. Doesn't matter which oxygen I use, right? You're going to get the same amount of formal charge in either of these positions, right? The double bond on the number 1 oxygen or the number 2 oxygen. So both drawings exist here. But in terms of affecting the geometry, yeah, you've got that lone pair pushing those bonded pairs down. Right? If I had 3 things around the central atom, maybe we 120, but since the lone pair pushes harder, this is going to be more like 117, something like that. And yeah, the lone pair is making this a certain type of bent geometry, right? There's going to be 2 types of bent. 2 bonded pair, 2 lone pair, or 2 bonded pair, 1 lone pair. So a different kind of bent, more like 120. or 117. All right, give the following electron domain and molecular geometries for the following molecules and ions. All right, so we're doing both, right? We're recognizing that there's a electron domain geometry, right, of all the electrons, and then the relationship of the atoms to each other, the molecular geometries. So we do the Lewis dot structure for hydrocyanic acid. We have a linear geometry around the central atom, and that's for both, right? All the electron domains and the bond and the arrangement of the atoms to each other, right? So it's a linear for both electron domain and molecular geometries. B, we do the Lewis dot structure for sulfite. We get a pyramidal geometry as far as the atoms are in relation to each other. But it's a tetrahedral arrangement of all the electron pairs, right? So we have that lone pair up there, so a tetrahedral geometry of all the electron pairs, a trigonal pyramidal for the molecule. C, when we do the Lewis dot structure for sulfur tetrafluoride, we end up with an extra pair of electrons around the sulfur, right? We're breaking the octet rule here. So that extra lone pair bends those bond pairs into a seesaw geometry of the atoms. And we have a trigonal pyramidal geometry of all the electron domains, right? The non-bonded electrons included. For for this anion, I'm not sure what you would call it, right? So PF6 minus. You have an octahedral geometry of both the electron domains and the geometry of the molecule. When we do the electron configuration for the E cation, or the cation, in letter E, we have this for the Lewis dot structure. And when we left out the positive, there'd be a positive formal charge on that nitrogen. Nonetheless, it's a tetrahedral arrangement of all the electron pairs, right? So again, around the central atom, 4 bonded pair, no lone pair. For nitrogen anion, we've got a linear geometry around the central atom, linear geometry of all the electron domains. All right, give the approximate values for the indicated bond angle for the following molecules. Okay, so if I have, for number 1, if I have 2 bonded pair, 2 lone pair, right, this is a bent geometry with a 105-degree bond angle. For number 2, you've got 3 bonded pair around the central atom and 1 lone pair, so this is going to be a trigonal pyramidal geometry, 107-degree bond angle. If we're looking at number 3, that's 4 bonded pair around the central atom, no lone pair. So that's tetrahedral geometry, 109.5. Again, with number 4, it's bent. With number 5, you've got 2 bonded pair, right? We treat the triple bond the same as a single bond. 180-degree bond angle, linear geometry. With number 6, we have the double bond and 2 single bonds, right? We treat the double bond repulsively like I would a single bond. So 120-degree bond angle there, right? A planar geometry. And with 7, 2 bonded pair, 2 lone pair around the central atom, that's going to be 105, bent geometry. And 4 bonded pair, no lone pair around the central atom with carbon is going to be 109.5-degree bond angle, right? A tetrahedral geometry around the center. So again, right, molecules with multiple centers, you got to look at each center in isolation in terms of the localized geometry. Predict whether each of the following molecules is polar or nonpolar. All right, so again, it all boils down to drawing a good Lewis dot structure, getting the geometry. Based on the fact that fluorine's more electronegative than iodine, the electron's getting pulled towards the fluorine and away from the iodine. So yeah, there'll be a positive side on the iodide side, and there'll be a negative side on the fluorine side. So polar. CS2, You draw the Lewis dot structure correctly. You're going to have a double bonded carbon as the central atom, two sulfurs on flanking on either side, 180-degree bond angle. Those dipole moments, right? The fact that the sulfur is more electronegative than the carbon cancel each other out, right? They're pulling in opposite directions. So there is no way to orientate the molecule. So you have a positive side or a negative side. So with a linear geometry with the same thing on each side, it's nonpolar. No negative side, no positive side of this molecule. Sulfur trioxide, same thing, right? When you do the Lewis dot structure for sulfur trioxide and predict the geometry, it's a planar trigonal geometry with the same thing at each corner. So these individual dipole moments cancel each other out. There's no way to orientate the molecule, so you have a negative side and a positive side. So nonpolar. Now with phosphorus trichloride, you have that extra electron pair, right, pushing those bonded pairs down. So the chlorines are on one side of the molecule, the phosphorus on the other. So electrons are pulled towards the chlorine and away from the phosphorus. So the negative side of this molecule will be the chlorine side, and the positive side will be the phosphorus side. So a polar molecule. Sulfur hexafluoride, all the individual dipole moments are pulling in different directions, so no way to orientate it, so you've got a negative side or positive side, so not polar. Iodine pentafluoride, you've got an extra electron pair around the iodine, right? So you have this square pyramidal geometry. So the fluorines are on one side, and the iodine is going to be on the other. So yeah, we'd have a overall dipole moment with this, the fluorine side being the negative side, the iodine being the positive side. So whether it's polar or not is going to have a lot to do with how this what kind of physical properties these molecules are going to have, what kind of chemical properties these molecules are going to have. So predicting whether it's polar or non-polar is an important part of this unit.